Okay, stop share. There we go.
Yeah, that worked. Okay. Dirk, could you start sharing your screen,
You?
please? Good. So, okay, the floor is yours.
All right. Thank you very much. Can you hear me okay?
Yeah, it's very good.
Okay, thank you. Yeah, thank you very much. Also, mainly for the invitation to be able to present some of our work here. So I think this is really a very exciting symposium, very inspiring talks that we already had and that are going to come. And it gives us the opportunity to present some of our work that relates to this interplay of surprise and rewards. And this project that I'm going to talk about, human belief, state-based exploration, exploitation in an information-selective symmetric reverse bandit task, that's part in a bigger, line of research that we've been following for a couple of years now, which we call agent-based behavioral modeling. And what we do there is, on the one hand, we perform cognitive psychology tasks and record human behavioral data in experiments. And in parallel, we develop artificial agents that work on the very same tasks as the humans do. And then we try to, by means of statistical embedding of this situation, arbitrate between different agent models to explain the behavioral data. So, so we are not really coming from a computer science perspective where we try to find the best agents or the most computationally efficient agents, but we use artificial agents to inspire computational theories of cognition. So that's so we have a couple of projects that work in this context. And on the other hand, we mean by agent-based behavioral modeling a conceptual framework that is closely related to the RL framework that we've also just seen in Professor Bartos' talk. So we usually distinguish a task model, so that corresponds to the environment that is usually has some dynamic states, parts of which may be observed by the agents, other parts which maybe not. We have agent models that observe parts of the state, form often belief states. So we often work with Bayesian agents that then form decisions and emit actions. And like in the talk that we've just seen, we also struggle a little bit with where to locate rewards or reward signals. So like we've just seen for us, there is an objective thing in the world that is the reward, but of course it depends how this is observed and how this is then proceed to form a reward signal that informs decision making. And finally, we embed these two components because we're trying to use this as a means to derive neurocognitive theories. We embed this in a data analysis model. And yeah, the project that I want to present as part of this ongoing initiative of agent-based behavioral modeling was conducted together with Lilla Horvath, a PhD student. And my aim is here to provide a general overview of this project. For all technical details, interested members of the audience are very invited to look at our preprint. There's also an OSF repository where you can find the data and the code. And we are currently revising this work for computational brain and behavior. So in this talk, I first would like to give you the general idea of the reinforcement learning scenario that we are studying here, which relates closely to these questions of reward and surprise and epistemic behavior that we touched upon already in the first part. Then I'm going to show you experimental data, so our experimental implementation and some descriptive statistics of human participants data. And in the third part, then show you how we specify our three models, and then conclude. So The information learning, reinforcement learning scenario that we are considering here is this thing that is in the relatively long title. So we are considering an information selective symmetric reversal bandit task. And what we basically mean by this is that agents, so human participants and artificial agents, learn about two possible actions, namely selecting a square or selecting a triangle. And one of these actions at a given point in time is likely positively rewarded, so has an 85% probability of yield a reward of +1. And one of them is likely negatively rewarded, so has a high probability, 85% of being detrimental and yield a reward of -1. The crucial, or one of the crucial manipulations here is that this is an information selective task. So the reward information can sometimes be observed and sometimes it can be not. And it's actually the task of the agent to also select whether they want an informative or non-informative action. The task is symmetric, so essentially it's more akin to a one-armed bandit than a two-armed bandit, because whenever you observe something about one action, this implies the symmetric negative for the other action, and it's a dynamic or reversal bandit task. So the state, so the action reward contingency changes at given time points in the over the course of the reinforcement learning scenario, and the agents have to learn anew. And here we are interested in three basic decision strategies. So on the one hand, we are interested in exploitative strategies. So select an action that is believed to be associated with a higher expected reward. This may be most closest to the primary reward signals that we were interested, that Professor Bartow talked about. And on the other hand, we're interested in explorative decision strategies that are most akin to epistemic behavior, as we heard in the first talk. So here the aim would be then to select an action that maximizes information gain, and we measure this in our modeling work as Bayesian surprise, as we will see. And then what we then also look at is a combination of these two goals by integrating them. So that's also part of our modeling initiative. So this kind of reinforcement learning, as I just described it, where you have actions that might be lucrative and you need to learn about them, and actions that might be informative or non-informative, is of course quite abstract. And we would, however, argue that these kind of choices and learning about how to make these choices actually play a role in the real world. So here, an example for that, of course, it involves COVID-19. So if you imagine a patient exhibiting COVID-19 symptoms, then this patient would, specifically in the early days of the pandemic, have basically two choices. So either they could home quarantine, which would be then related to the reward that the transmission rate, maybe it's a societal reward, that the transmission rate would be kept down, but the information about the infectious state of this individual would be missing. So this would be a kind of a lucrative non-informative action. On the other hand, the patient could decide to obtain a medically administered PCR COVID test, but for this would have to go out to the world and possibly increase the transmission rate. So this is one of the examples. Of course, you can come up with many other examples where you might have to choose between something that you think is rewarding but doesn't give you information at this point, or something that is not rewarding, detrimental, but maybe informative. So that's the overall reinforcement learning scenario. So the question of how to choose between lucrative and informative or non-informative, and detrimental and non-informative or informative actions. How did we do this in experiments, and how do our participants perform there? So overall, we had an experimental design where we manipulated the lucrativeness of the action as a lucrative or detrimental action, which is here in this figure signaled by the color of the symbols. So yellow here meaning the lucrative action, but this could of course change. So as our bandit was reversing at a given point in time, the triangle would become the lucrative action. And on the other hand, we have this informativeness of the action, which was signaled by a dark or a light gray background. So the dark background of the shape that is to be selected, always signaling that this is an informative action, and the gray background a non-informative action. And then participants and the artificial agents were exposed to these choice problems in two trial types. One trial type 1, being the relatively simple decision between a lucrative and informative action. So if the square would be believed to be lucrative at this point, then here the square and the black background, versus a detrimental and non-informative action, where of course it's very intuitive that lucrative and informative is better than detrimental and non-informative. On the other hand, we had trial type 2, where participants or agents were supposed to choose between a lucrative and non-informative action or detrimental and informative action. So this is the two trial types in which these various action choices were presented. And then from the perspective of participants, and then also the artificial agents, on a given trial of this task, of course, people don't know which of the two shapes is currently lucrative. So this is why they are white here. But they see the background, so whether it's an informative or non-informative action. And if a participant, for example, here in the upper row selects the informative action, so the black background, then the reward would be played out, and the action outcome would be presented to the participant as a $ or a crossed out $ for the rewards plus and -1. However, if the participant or agent chooses the non-informative action here on the light gray background, then although the reward would be played out, it would not be observed. So we have a dissociation between observations and rewards here, because here both in the plus and the -1 reward would be mapped onto the question mark and not be observed. And then finally, over the course of the experiment, the state of the environment or the state action reward contingency of the environment changed. So in the beginning here, for example, the square would be lucrative and the triangle would be detrimental. And after a number of trials, this would change so that the square would be the detrimental action and the triangle would be the lucrative action. And then people would essentially relearn this mapping from actions to reward. Now, how does the human behavior look on this task? So here we have data from 24 participants who performed 2 runs of this task. So this here shows 1 run of 80 trials, and people performed 2 runs. If we first look at the average choice rates over all trials, then on trial type 1, where people were to choose between a lucrative and informative action and a detrimental and non-informative action, clearly the lucrative informative action was preferred, as one also would expect. On trial type 2, where a lucrative non-informative action was contrapositioned with a detrimental and informative action, the benefit of the lucrativeness of the action was diminished, or the people chose the detrimental and informative action more often than just the detrimental and non-informative action. So signaling that participants were actually interested in learning and getting the information, so that there's a clear preference for information. Of course, these are average choice rates over the entire experiment, and this is then collapsed over all the reversals. So the full data set, given that all participants were actually presented with the same order of choices, then looks in terms of the choice rates like this, where you can see as the gray lines always reversals of the lucrative shape. And one can see that after a state action reward contingency reversal, the people could then again learn and resolve the uncertainty to learn which is the lucrative shape. And this can, of course, be looked at a little bit cleaner if we reversal lock the choice rate. So here we see after each reversal the choice rate for the lucrative and informative action and the lucrative and non-informative action. So the lucrative and informative action is generally preferred over the corresponding complementary detrimental non-informative action, except for in the very beginning. And what happens, although at least to a certain degree, is that the difference between the informative and the non-informative action decreases as learning proceeds. So as people learn over these trials after a state reversal, which action is lucrative, the benefit of using the or choosing the informative action slightly decreases, which is shown here in this delta reversal locked choice rate. So there, as people become clear about which is now the currently lucrative action, they choose the informative action less. So that's the behavioral data. So that's how we did, or how we implemented this reinforcement learning scenario in a behavioral experiment. And in the next part of the talk, I want to then now describe how we map this to our artificial agent and our model comparison scheme. So again, when we formalize models in this agent-based behavioral modeling approach, we distinguish task and environments models, which are just the formalization of the reinforcement learning scenario of the task. Then our agent models, which which we view as computational cognitive theories, and then a data analysis model, which embeds this interaction between the task and the agent and allows us to arbitrate between different agent models to explain human behavior. Our task model and all our models we usually write as these tuples, which are inspired by, but not often not quite identical to partially observable Markov decision processes. So in the current project, the task model featured a set of partially observable states where the first state component signaled the currently higher rewarded shape, so the state action reward contingency, and the second, and this was not observable for the agent, so this was of course a part of the environment, but not directly observable for the participant or the agent. And the second state component, which was observable for the participants, were the available actions on a given trial, so the informative or non-informative and square and triangle actions. Yeah, A is our set of actions, so the square and triangle crossed with the informative and non-informative background signals. A set of rewards, which was played out according to a state action dependent reward distribution, but which was not directly observable for the agent and the participants. But what was observable were obviously the dollar sign, the crossed out dollar sign, and the question mark. The final two components are kind of functional aspects of the task model. So one is a deterministic state evolution function. So all participants were presented with the same order of states. So there was no sampling in the environment in terms of the states. And then crucially, the task model involved an observation function which mapped the chosen action and the observed reward to the observation that the agent makes. So for informative action, so selecting the black background, the then sampled reward was then either mapped, if it's a +1, to the dollar sign, or the -1 to the crossed out dollar sign. And for non-informative actions, both rewards were mapped to the question mark. And so what we have here is a dissociation of the observations that the agents can make and the external reward. So again, referring to this masking or information withdrawal for certain actions. Now, based on this task model, we then formulated our agent models, and we here chose an agent model space comprising 5 agents, 2 control agents, a random choice agent, and a win, stay, lose, shift heuristic agents. So I will not go into more details about these 2 agents, but rather focus on the 3 agents that, based on a belief state, then implement the decision policies that we are interested in. So exploitative behavior, explorative behavior, so epistemic behavior, and the combination in a hybrid model. Now, our agent models usually comprise many aspects of the task. So this then reflects the fact that, of course, participants were informed explicitly about certain aspects of the task. For example, that there could be that there are different actions, that there are the observations that they can make, and so on. So we take certain parts of the task into the agent model as well, and then our Bayesian models encode an action-dependent generative observation model. So the agents represent uncertainty over the unobservable state, which is our first state component, and so they have a prior, they have a state-state transition probability, and they have a action-dependent observation likelihood. And based on this, based on these distributions, or these distributions together, of course, specify a joint distribution over the unobservable state components and the observations, from which factorizes according to the conditional independencies that are encoded in these individual distributions, which we can then use to evaluate the belief state of the agent. So to evaluate the probability distribution over the first state components given all previous observations and actions in a given run. And essentially this is just the application of Bayes' theorem here in the form that many of you, of course, are familiar with in the POMDP action dependent manner. And this we can this then yields essentially a belief state random variable, which is the probability that the unobserved state equals 1 given all previous observations and actions. So the probability that the square is currently lucrative. And this can relatively easily be implemented in a stochastic matrix multiplication manner. Now, this is what all of these agents encode. So this is basically the basic machinery of these Bayesian agents. And crucially, to differentiate different behaviors, we then define action valence functions and decision functions. And by action valence functions, we mean functions that take the current belief of the agent about the unobservable state component and an action and put a number to it according to a given rule that we will look at in a second. And by a decision function, we mean then the idea of maximizing the action valence by selecting the action that currently holds the largest valence. Now, crucially, to implement our different decision policies that we are interested in, so exploitative, explorative, and hybrid behavior, we then define these action valence functions, which I think now, after hearing the first talk, might actually relate to internal reward signals, but this might be something maybe for the discussion, because if we think about the action valence function for the exploitative agent, what we are using there is the expected reward of an action under a current belief state. So we're looking at the conditional expectation of the reward. So we assume that the agent knows the reward distribution, but of course this is action dependent. We're looking at the conditional expectation weighted by the probability to be in the given state on which this expectation is conditioned in. So we're weighting the expected reward by the belief state, and that's what the exploitative agent assigns as an action valence. For the exploitative agent, we use the expected Bayesian surprise of an action under the current belief state. So the KL divergence between the current belief state and the possible belief state that the agent can assume or can get into if the agent makes a given or emits a given action and averaged over all possible observations. So here is where this notion of surprise comes in. So essentially the exploitative agent wants to maximize, together with the decision function, wants to maximize the surprise, so the update of their belief state. And finally, we use an exploitative agent to explain the human behavior by just a convex combination of the action valences of our first agent and our second agent. So one way to look at these agents is to look at the action valence as a function of belief state. So if we look at the exploitative agent, if the belief state encode the probability by which the agent thinks that the square is lucrative, we see that as the belief in this increases, the valence of this action increases linearly as well, and the triangle valence goes down. The explorative agent, crucially, always prefers the informative action. So the action that is signaled by the black background, and prefers that most or has the highest preference for it if the uncertainty is highest, so if the belief state is at 0.5. And if we now combine these, for example, in agent A3 with a convex combination parameter of 0.25, we see that the explorative goal of this agent shifts the breaking point, or the point where one of the decision, where one of the actions has the higher action valence to the left, so to a lower belief. So because this is also, because here the black square is also the informative action, this becomes better than the other action earlier than in the pure exploitative scenario. Now, these are our agents, and then to bring them together with the experiment, we embed them in an analysis model where we define a conditional action likelihood, so the probability for emitting a given action based on all previous action and observations, for which we use the softmax, where the tau parameter determines how much the valences are basically equaled out. So the larger the tau parameter, the more likely become the actions, even if the valences are quite different. So we interpret this tau here as post-decision noise, because even if the valences are very different and tau is very large, the agents emit the same actions. And then we use a numerical maximum conditional log likelihood scheme to estimate the free parameters of the agents, which are the tau parameter, and for our A3 agent, which combines both explorative and exploitative goals, it's also the lambda parameter. But these are quite few parameters, so it's not a highly these are not highly parameterized models. And as readouts for the performance of the models, we then use on the participant level the BIC, where we, of course, penalize the number of free parameters, and on the second level use a random effects Bayesian model selection scheme proposed by Rigu et al. That yields protected model exceedance probabilities that tell us how much more likely one model of our model set is over the other ones. Now, how much time do I have left? Sorry.
You've got another 6 minutes or so.
Okay.
Oh, no, sorry. Yeah, no, something like this.
Okay, thank you. Then I can briefly show you also the model validation results. So having embedded the agent and the task in the statistical analysis model, we can, of course, perform simulations and check whether we can actually identify our models based on the data that they generate. So here we have data generated from all our 5 agent models, so C1, C2, A1, A2, and A3, and we look at for the same circumstances as our experiment implemented, we look at how well our posterior how our protected exceedance probability is able to recover the generating agent, and that works fairly well for C1, C2, and A1. Here we, of course, for the agents that encode or that are augmented with the softmax parameter, we have to take into account that the higher this noise parameter, of course, the noisier the data, so the harder the identifiability is, but it's still working for also our exploratory and our hybrid model in scenarios where the noise is rather low. So this gives us some confidence that we can actually arbitrate between the different agent models based on experimental data. And we do something similar for the parameters, but I will skip that and come to then the results. So what we see here is first the cumulative BICs for our different agent models based on the experimental data that the human participants data that I've shown you in the first part of the talk. And what we see is that the random choice agent does not explain the data too well. The purely exploratory agent, so the agent that just prefers informative decisions, also doesn't perform that well, which is also to be expected, because after all, participants were also instructed to maximize the rewards. However, the purely exploitative agent is still outperformed by the hybrid agent. So the hybrid agent that takes into account also explorative informative goals performs better, which is in line with the fact that we saw earlier that informative actions are often then preferred. So that's at the cumulative PIC level. This is fairly consistent over participants. So if we look at the second level, then the protected exceedance probability for our A3 model is clearly dominating all the other agents. And based on then the group average parameter estimates, which, for example, for our tau parameter are in a part of parameter space where model identifiability is working, and our convex combination parameter corresponding to this lambda of 0.25, where I showed you how this looks in the belief state dependent action valence. Based on these, we can then again generate experimental data and compare that to our observed participants data, which is shown here. So in the background, you have again the observed reversal log choice rates for lucrative and informative and lucrative and non-informative actions. And our simulations are then very much in line. So our artificial agents based on these parameters can regenerate the patterns of the human behavior that we observed, both in this way of looking at it and in looking at the difference. So that would be then almost it. So I showed you as an example for agent-based behavioral modeling approach, a reinforcement learning scenario where we basically are interested not only in maximizing reward, but also taking the question of do people want informative action or non-informative actions into account. And we see that in this task, humans prefer informative actions, and they do specifically if they're most uncertain, which is quite naturally, but it's actually found in the behavioral data. We use expected Bayesian surprise as a formal measure of action information gain or as a driving force for epistemic behavior here. And we find that combining in this task, combining expected reward and expected surprise maximization to explain the human data best. So in summary, this is kind of one of the projects that we're currently doing, where we try to look into the reinforcement learning literature as an inspiration for explaining human cognition, but then also having to deal with other problems that like how we infer on these interactions that in pure AI might not be that on the forefront. So thank you very much, and I'm looking forward to any questions and of course the other talks.
Thank you very much, Dirk. Thank you. Let's start with the questions. Here is our first question by Simona Garoppio, and she asked, do participants also learn about the metastructure of the task? For example, after how many trials the subjects have to expect a switch in the reward?
Yeah, that's a very good question. No, they actually don't. So this is also why we could assume that, or why we could specify the state transition probability explicitly for the agents. They were told that there's going to be a switch 4 times roughly, 3 or 4 times during a run. So we assumed that these parameters are known to the agent and also known to the participant. Of course, one could also have these as free parameters in the agent models, but of course, this would also make the inference then again more difficult. But we here assume explicitly that the agent know these because the human participants were informed about this.
Thank you. I think that answered the question quite clearly.
We have a second question by Kenji Kobayashi. Is it possible that the behavior reflects ambiguity aversion as opposed to exploration information seeking?
Oh, that's a good question. Or there I would have to think closely again about when something is more ambiguous rather than I have to think about my neuroeconomics and the definition of ambiguity there. So in principle, I would rather think not, because it's fairly clearly communicated that yeah, this can give information. And okay, so the basic choice conflict that participants face is that at a certain point during the experiment, they will be quite certain that now a certain shape is lucrative, and then if they find that this lucrative action is paired with no information, and as opposed to an action that might be detrimental but with information, then they would also go for the lucrative action which doesn't have information attached. So it's a good question. I don't have a clear answer, but I would, because it's so clear that it's can get you information. Yeah, I don't have a good answer. Sorry.
Okay. Sometimes no answer is also an answer. Okay, here we have another question by Lucas. And he asked, would any of the computational models used have the power to learn about the volatility of the environment, like typical hierarchical Bayesian models?
Yeah, so they, this is...
Stop. And would you regard such inference as useful or not?
Yeah, I mean, this is closely related to the first question. So the volatility of the environment, so in this case, how quickly the state changes, or maybe super or meta structures on this, so how quickly the changing of the changes of the state changes. This is included in this state transition probability, because if this is low for a change, then of course this corresponds to a fairly stable environment. And this of course can be parameterized and could be learned, but like I said regarding the first question, we assume that this is given to participants. Of course it could be, I mean, it just creates another free parameter in the model that is nested, which then needs to be taken care of in the inference procedure.
Johanni, are you?
Yes, we have a question by Davide Bella. Is there a strategy metric to compare agent models and determine how general or complex they are? That is the number and diversity of reward signals they have processed along their learning history?
That's a good question, because it relates to the question of model comparison. And so what I can say here is that we use kind of the classical approach in computational behavioral modeling to penalize the number of free parameters. So if you have more free parameters, you can of course tailor the agent behavior closer to what you observed. There is this other level of describing the complexity of models, which yeah, goes beyond the fact of how many free parameters they have. This is not something that we took into account here, but it's an interesting question. I mean, this is also, I mean, this whole thing about penalizing free parameters. In a way, we also develop these agents as, of course, as theories for human cognition. And then it's also about sometimes just from the experimental's perspective, as that some models are more interesting than others. So for example, we assume here belief state based decision making. Of course, one can also create models as, for example, the Swin-Stay-Lose shift heuristic that are belief state free. But we are interested in this these Bayesian belief state models because we reason that humans reason in this way. And of course, there are more model comparison and complexity penalization schemes, but I think this is also something that yeah, can still further be developed. I mean, it's more, this is then, and in the end, it's also a utility function. What kind of scientific theories you would like to encourage? So, and I think the pure number of free parameters is, of course, a bit lame. And what the audience member suggested sounds interesting, but it's not done here.
Okay, we got one more, maybe last question by Martin Remy Berry. And he asked, lucrative action can highly be driven by society-driven choice making. So the question is, can you ensure that these choice actions are natural decisions?
Yeah, I mean, this is one of the assumptions that always go into this kind of laboratory task. So if you do tasks with human participants, there is always the assumption that people actually want to maximize, in this case, the monetary reward and then trade whether they actually want information or not. Sure, that's an assumption, but otherwise it would also be quite hard to start this whole comparing agents and humans at all without this assumption, because of course we can assume, okay, if these are students, they are not interested, so the participants, they are not interested in everything. This is also a choice strategy, yeah, we don't think that this is the choice strategy, so that people are not interested in anything, that this is a general choice strategy that people use in the world. And what we've seen from Professor Bartu's talk, of course, there are evolutionary pressures to maximize certain intrinsic reward signals. And so we kind of use this monetary reward as a proxy for that. Of course, it's context dependent. This was also, of course, the point. It may be the case that something like this issues an internal reward signal, or maybe not. But yeah, so we use it as a proxy, and in general, in these monetary rewarded schemes, we assume that the participants would like to make some money.
Okay, thank you very much once more, Dirk. I think we are 4 minutes over time. Thanks very much for the wonderful presentation and for your very clear answers to the questions.
Thank you.
For all of you, we will be back in, say,